Hey folks, this is Pramod from the CoinOp collection. So today, I'm going to go over some prerequisite tooling that you're going to be needing in advance of some of the learning code bases that we're going to release. Now, the first one we're going to be releasing is Double Dragon 3, which is part of the Technos 16 cores we did last year. And basically, these were cores that we did for the Pocket and also the Mister a little bit later on. And these cores are basically in a pretty finished state. Like we're not we've fixed over the past few weeks the final issues with it, and also converted it to K3, which is our framework that we're also releasing along with these projects as well. Um, and we fixed the final few issues in the past few weeks, and we are not doing any more work on the Techno 16 platform. We're going to be releasing these. Now, one thing that you will notice when we do release them is that they are not the normal GPL license. And the reason for that is because primarily I want these works to be a stepping stone for different creations and different sorts of improvements in the future and research, as part of the platform workings. I don't want to tie people down to necessarily using this as a standard. And I think that was one of the sticking points about GPL. For me anyway, it's primarily geared towards open source, which is not really something that we're primarily interested in. I mean, it's good to do, but it's not something that we're primarily interested in. Normally, we do these things for fun and for a hobby, and so we don't really make any money off of these. We just kind of just like solving really difficult problems and seeing how accurate we can get to the board. And we primarily do these for fun. And so, like Creative Commons, which is something that I've picked up in some of the Mister repos that are using that license. And so, Creative Commons is what we're going to be releasing. Most of these, actually all of these, as when it pertains to our code, and every single part we have redone pretty much because uh, we had to redo the whole thing because we're no longer licensing JTFrame. We used to use JTFrame for many years. We spent a lot, especially me. I mean, I spent a lot of time fixing it because a lot of it doesn't really work properly, right? Not especially for not the stuff that we use it for. Obviously, we're no longer licensing that, for obvious reasons. And so we worked very hard to create our own framework this year. And our own framework has the complete set of bells and whistles that we use. We have our own high power SDRAM controller that is actually a different approach than anyone is using nowadays. Like most of the SDRAM controllers that you see out there are based around fixed burst. This SDRAM controller is more high powered. It has automatic caching built in, and it has an easy way for you to just kind of plug in and just use it. You don't really have to think about too much. You certainly don't need like to play around with shifted clocks or that sort of thing that you normally would have to with other SDRAM controllers. And you can get any number of bits out that you want, right? You don't have to do your stuff in 32-bit widths or 16-bit widths or 64. You can get 128 if you want to. You can clear a whole page if you want to. And that was a requirement for some of the other cores that I do, for example, Midway, and also the CPS3. That's a requirement for some of the cores that are really high powered that I need a high bandwidth for. And so I wrote this new controller that is a fundamentally different approach that I thought was a good approach because I had gone through Midway, and That's exactly what I implemented in the JTFrame controller, the SDRAM controller. And obviously, I'm no longer using JTFrame, so I just made my own. That's more. It's even more aggressive towards this approach, and it's interleaved too. So not only do you get interleaving, but you get variable burst based widths. Okay, and then so that's that. I have some audio support. So I wrote the X6295, which is your standard Oki chip that's used for 80 PCM. We use Rocky's. Rocky's an excellent developer, by the way. He's from Korea, and we work with him pretty often. He has supplied a really good die shot based YM2151. We've tested it extensively on many releases. Actually appears in the Cave core, I think, as of the latest, or it will appear next week or so when we release a new core on the Cave thing, which is I'm working on Sailor Moon right now. So basically, we'll release that, and I think well, obviously this Double Dragon 3 one will have Rocky's core. It's an excellent core. It's very accurate. The sounds sound good, and that's what I'm looking for. In addition to that, we also have some simulation-based tooling. So primarily, okay. So wait, let's hold off on that. I'll go through that in a minute when I start going over the tooling. So okay, so just to kind of give you an overview. So primarily, um, my workflow is a simulation-based workflow. So primarily, I'm not working on the FPGA device, and I do builds, but not. And there are some issues, and sometimes when I do projects like with trial and error, like I'll just keep building and trying different things. That there are times when I have to do that, especially recently. I've taken over the Cave stuff. The Cave is obviously written in something different, and then I had ported some of it to Verilog. Then I rewrote most of it in Verilog. So it's a Verilog based core now. I even rewrote most of the core stuff in Verilog, and rewrote it like brand new, like from scratch. Like I did the research and did everything from the ground up for some of the main stuff going on, like the CPU, the sound, like all the subsystems. So the core subsystem processing I redid, and so I a lot of the time and that project I completely did with trial and error. Like I didn't have any simulation benches then. When we started a few weeks ago with ramping up K3 to be more polished, I started instrumenting K3 to have different simulation benches. So now, no matter what sort of core you're doing, whether it's a port of something, as long as the top level K3 interface stays the same, like you can literally copy and paste your core in there, the simulation benches will hold, right? So I can literally like copy and paste something or some core into K3, or I can start a new core in K3, and I can run the same simulation benches that I would normally run, and they will work. Um, so I'll show you that in a minute. And basically, other than that, that's a basic overview. So we're gonna release Double Dragon 3 pretty soon. A-Track is currently working on it. He's currently working on polishing the directory structures, making sure all the stuff is appropriate for release, that it's high quality, because we don't want to release something that like no one will like, right? We don't want to release something that nobody's gonna be able to learn from or like reference. Like we don't just want to check a box and say, oh, we'll release something. That's the total opposite goal of what we want to do. We want to release something that's meaningful, that people can learn from, and also that can serve people well, as an example, right? Okay, and use it as a stepping stone for learning. Okay, All right, so let's get into the tooling that you're going to need. Okay, so obviously, I have Visual Studio Code up. Primarily, you're going to want to use Visual Studio Code, okay, as your IDE for Verilog. And if you go to the Plugins tab, you're going to notice there's some plugins related to Verilog that I have. You don't need anything fancy. What I use is this one here, or these two. I use these two. Verilog, Blue Spec. This is like the most used. I mean, something pretty standard. I used to use something else called Teros, and it's fine. It does a few extra things that you might find useful, but like I don't know why it just stopped. It's not that it stopped working for me. It just like did like as of the recent update, it does some like heavy linting thing, and it generates warnings that that are just not legit. Like it doesn't it's gone worse. I don't know why it is, but it's just gotten worse. It's very good. You can use it. It's just that I don't prefer to use that anymore. I just prefer to use the normal Verilog thing just for syntax highlighting and that sort of thing. That's all. That's the only thing I use it for. Now, if you have AI tooling, that would be good, right? So I have Copilot integrated, so you're going to see GitHub Copilot, right? And basically, GitHub Copilot is free now. I think it's free. I have the paid version, obviously. But like basically, GitHub Copilot is completely free for use, and I think you can upgrade it. Obviously, you can upgrade it to a paid version. But basically, it's the same. It's almost the same. I think you just don't get access to some beta models or something. What I recommend using if you do use this road, and I've said it in the last video, is that if you're going to use like AI tooling to do anything, just make sure you're grounded in the subject matter you're using it for, because AI can obviously like make stuff up, right? And that happens very frequently. So you have to be in a position to tell when it's leading you down the wrong path and to, correct it or steer it in the right direction. Or you have to just like basically discard it and start anew, right? So that can happen obviously with AI tooling, and sometimes it just generates wrong code, right? That's a fact. So you have to obviously have good knowledge in the subject matter under which you're using it for, and you have to have a good command over that, I think. But if you do have those two prerequisite things, then I fully support using AI for any of your projects. You can also use it as a learning tool. So I primarily use AI for boilerplate type of stuff, or for like code completion. Um, but a lot of the time, I find myself using AI for research purposes. So um, if I am researching a problem, I will often consult AI on the best the way to do things, right? Because I think if you do Google searches like I normally would have done a few years ago before the tooling, um, which is how I made many of the more complicated cores like Midway and Rising. This was before AI tooling. I didn't have any AI tooling actually, and I was a beginner. So I would just do Google searches and try to figure out and I would look at other cores to figure out how people would do this stuff, and I would just kind of learn from there. AI can actually accelerate your learning by bringing ideas to the forefront that you normally would not be exposed to if you just were limited to Google search, right? So you can learn faster. And I fully support it for that use case. I fully support it for enhancing your learning and enhancing your understanding of things. I use it for data analysis a lot of the time, because a lot of the time, like research, I mean, especially if you're doing a core, is data analysis. I mean, it's all data analysis. It's all black box testing. Like it's all that sort of thing. Like you're taking captures from the board sometimes. Sometimes you're working in an emulator, a current working emulator, whether that be Maim or something else. Um, I usually use Final Burn Neo because I like the way it's laid out. I am very used to it. I can load it in Visual Studio and I can use it. It's tooling that I currently use. So I use that a lot for research into current platforms and platforms that I am working on for the future. I usually mess around with the emulator. I usually try to learn the system. By doing that, I try to break anything. I try to inspect the RAM, inspect the data, see if there's a pattern to it. Like there's lots of different things that I do from a research perspective, and I think AI accelerates that. And so that's what I recommend. Okay, so you have that. You have the GitHub Copilot. One more thing you're going to need is Python. Python, I'm going to show you the plugin here that I use. I just use the regular old plugin for Python. I don't even run Python here. I run in the console, in the terminal. I'll run Python. But the tooling that I'm going to be supplying has some Python scripts in it. So, for example, for simulations, let me see here. Oh no, not that one. For simulations, maybe it's in modules. Let me see here. Let me see. It's in sim scripts. Okay, so you see these scripts right here. Maybe I'll just make this a little bigger so you can see it. Whoa. Okay. So you see these scripts right here. These are scripts that I use to generate data formats. So, like for example, this bin2 hex 8 as an example. What this does is it takes a binary file and converts it to a hex text file that is separated by bytes. This script bin2 hex 8 dual takes a normal file and it separates the even and the odd bytes, and you can use this when you have interleaved memory structures, right? And then this bin2 hex 16 does the same thing, but only it outputs 16-bit words at a time, right, in each block. So these are used to load data or convert data to different formats in your simulation, and that's very important that you have the ability to import data, because often at times what you're going to do is you're going to, like, let's say you have a problem, right? You're trying to research your problem. And basically, you can get up to that point in any emulator. You can use Final Burn Neo, you can use Maim, and you can do memory dumps. So if you do a memory dump, you're dumping out the state of the system for the most part. Now, there are nuances to that, right? So, like, you're not dumping out the state of the processors, right? Like if you're using a 68K or a Z80 or something like that, right? Those are a little bit more complicated to dump out. And also, you have to consider like any registers that you might have to dump out. So, like if you're trying to do this with the video system, and normally I would do this technique with the video system, but like basically, what you can do is you can dump out the video memories, right? Like you have scroll RAM, sprite RAM, and that sort of thing. You can dump them out, and you can use the test bench to isolate your video chain and make sure your video logic works on that frame. And you can use this to resolve like pixel rendering bugs. You can use it to isolate like scaling bugs. Like if the thing that you're doing supports zooming or scaling, you can do it that way. And these scripts will convert your data to a format that's used by the test bench, and the test bench can load it in to your memories. That's that. And then also, like, I have this other thing called frame export. So like when you're running when you're doing a core in simulation, it's very important that you are able to see the video output of what you're doing, right? So like if you want to determine if something boots, you want to see what the sequence of frames are that it uses to boot. If it's booting at all, are you getting video, that sort of thing. That's what these scripts do. And these scripts integrate with the Verilog test bench. And what they do is, so the Verilog test bench, it provides a byte stream to a file called video.raw. And basically what this does is convert that to PNG images. So you can see the PNG images automatically as you're running your test bench. You don't have to run any scripts. This integrates entirely using system commands. Okay. So that's what those are for. So you're gonna want Python. So Python is something that I use very frequently for scripting. These are your test benches. So obviously they're written in Verilog. Let me see here. Yeah, so you need Visual Studio Code. You need Python. You need let me see. GPT is optional, I would say, or Copilot. You don't necessarily need it, but it's helpful if you do have it. But do not, if you're a beginner, do not rely upon it. That's all I can say. Have like very strong competency in what you're using it for. I will say that again. I'll say that in like 50 times, and I'm sure nobody will listen to me, but I'll say it like 50 times. But you must have competency, heavy competency in the subject matter you're using it for. Otherwise, you're going to find yourself in really big trouble. That's all I can say. Okay. All right. So that's the tooling that you need for writing code. Now let's talk about what tooling you need to build the code, right? So for that, I have Cortis Prime. So the version that I use is 22.1. That's normally the version I use. I don't think you're necessarily tied to this version. I think you can use a newer version if one exists, but I usually use version 21.1. And so what this tool does is it does a bunch of things. Like, yes, you can compile stuff and you can build RBFs. So RBF is the thing that you need to build to make it work on the FPGA target device, right? That is a bit stream, right, that you need to program with. And it has a bunch of other stuff too. So like there's a timing analyzer, for example, right, which you can use to solve timing related issues if your static timing analysis is wrong or it's off, it's failing, right? You can use that to diagnose things. What I use, okay, I'll tell you what I use. I use the timing analyzer frequently, okay? I use signal tap sometimes because, like I said, my workflow involves doing things in a test bench, right? If hooking up signal tap helps me understand the problem, like if I can't get it, if I don't know what the state is, there are some issues that arise because I'm getting different results on the FPGA device versus simulation, right? And so what I do is I use signal tap to gain an understanding of what the state is of the problem, the state is of the core for the problem I am researching. That's what I use it for. I don't use it like okay, so there are some people out there who use signal tap extensively. That is the only thing they use. They don't even do simulation, actually. There's some people who do that, right? I know of those people, and they are good at what they do. I'm not saying that's wrong. That is perfectly legit. You can do that. I'm just saying that's not the way that I work. Okay. I think Kevin from Analog, he uses signal tap extensively. This is the only thing he uses. He's legit. He has obviously a lot more FPGA experience than me. And he's wonderful. He uses that, and that works for him. He runs simulations. I mean, not simulations, but he runs like signal tap stuff for like a week to determine metastability issues and all that stuff. And he's very good at that, and he does it. He's wonderful. You can certainly do that if you like. I'm just saying that that's not what I like. Okay, and what I use signal tap for is very minimal. It's just to determine the state of the problem that I'm researching. That's it. That's the only thing I want. So if something's not working right on my core when I build the core and I start running it on the target device and I'm not seeing what I like and it's not matching what's in simulation, my first inclination would be to get those signals in signal tap, deploy that, and then monitor that. Right? Not only monitor it, but like just take data at time points. I'll take the data and see, oh, what's the state of the data? Is the data making it to point B? What's the state of this part or that part, what state of the CPU, what state of the audio. Like I want to know what the current state is so that I can get more information to resolve the problem. But ultimately, I will resolve that problem and try to reproduce it either in um, either in a simulation, or I will use it and reproduce. I'll try to reproduce the problem in a current emulator. Okay, so that's what I use Signal Tap for. You're going to find yourself using the PLL editor, which is a part of the IP catalog, right? So when I show you PLLs, when we go to that area, we'll talk about PLLs. So I'll just show you this PLL. And what is a PLL? Well, on the FPGA device, there are clocks, right? Raw clocks that come in. And basically, you have to get clock outputs that are for your system, right? So this Technos core uses this clock is actually not used anymore. This used to be used when we use JTFrame, because JTFrame, the SDRAM controller, requires a shifted clock, which is it's a phase shifted clock for your SDRAM controller. But this core just requires the main system clock because I use the Alt-DDIO to generate the shifted stuff for the SDRAM chip. So no shifted external clock is needed. Okay. Okay, so this is a 98 megahertz clock. So what does that do? Okay, so anything that you're doing with FPGA needs clocks. Okay, needs clocks to function. Clocks determine the speed of your overall system and logic. Now, normally what we do is we create one master clock, and what we do is create clock enables to gate the speed of that master clock to adapt it to different sections of the core. So, for example, we certainly do not run a 68K processor at 98 megahertz, obviously, right? For this core, I think it's like 10 megahertz we run it at. And so we'd have to divide this 98 megahertz clock and gate it at the proper speed, and then run the logic at that. And usually for most cores, that is 2 times the effective rate. So, for example, if it's 10 megahertz, you're going to create a 20 megahertz clock enable. And the reason for that, for the most part, is that the chips that you see in the old days utilized different cycle phases of the clock. So, like, they'll use like the positive and negative edge of a clock to do stuff, right? And have different phases, as opposed to just the positive edge, right? That we normally synchronize on. So that is primarily the reason, because there's different phases, and sometimes that actually is part of the specification. Like if you take a look at the 6809, even the 68K, right? The 6809 has a 4-phase clock cycle, like they have the Q and the E, right? And those trigger, like the pulses of those trigger, or the waveforms of the clock, the legit clock, trigger different phases within the processor. Like one phase triggers like a LU activity. One phase will trigger bus activity and bus or memory writes or reads, and that sort of thing. You have to monitor for those changes and do stuff, right? So anyway, long story short, that requires a 4 times effective clock, right? Because it's 4 phases that you're trying to do. Okay, so anyway, that's clocks. So you're going to want to generate a master system clock. Now, all that's required is that there are some IP out there that you may use that will require another clock, so you can add as many clocks as you want. K3 has a way to adapt to your PLL, and so you can pass through any number of clocks that this supports. And I think you can have in this chip, this Cyclone 5, you can have 9, right? So you can have up to 9 clocks that you pass through to your core. I generally don't use more than 1, but knock yourself out. Actually, I think for one of the cores I experimentally did, I did like 3 or 4, because there were like 4 different things, 4 different clocks that I needed, and so like the way that's treated is those are separate clock domains, right? And you may have to synchronize between them. You may have to. Depends on what you're using it for. But like, yeah, you may have to get into a synchronization situation. Okay. All right, so that's that. That's the PLL editor, and which is part of the IP catalog, which is what you'll see on the side. I generally don't use much Intel IP. I think the Alt DDIO is something that I use, and the PLL obviously those are the two things that I really use. The rest of it is all synthesized, regular vanilla Verilog. Like I don't use like oh actually you know what for the cave thing I do only because Josh uses it. I carried over one of the memory IPs because it has a weird requirement. Like there's one of the memories that he has in the cave core where like um the ports are different lengths. So like in one it's a dual port memory, but like one of the ports is a wider bit width than the other. Like one of them is like something crazy, like it's 128 bits wide, and the other port is like 32 or something like that. So the interface to the CPU is like 32, or maybe it's 16. I don't remember which one it is, but like basically, you can't really do that. I mean, I guess you could. It's very just very strange to do it in regular Verilog. And actually, I don't think it even synthesizes properly. So anyway, you can't do it. I tried and you can't do it. So the only way you can possibly do it is by taking this RAM IP from Intel and wrapping your stuff around it. That's the only way I've found to do it properly. Otherwise, it doesn't work, right? So he's got some crazy thing in there. That's the only thing I've retained. Like that's the only real Intel IP. I mean, even in a core that I would do, I would not use that. I think that's just some separate use case that he had. Normally, if I had a consolidation or a caching situation, no, I mean I wouldn't call it caching. I would call it consolidation because like you know what a lot of people do is if you have like hardware sprites and you have a sprite format, what you want to do and those span multiple addresses, right? Like so like your RAM format might be like 64 bits or 128 bits, right? And those are all the properties of the sprite. Like you have your X position, your Y position, your zooming, or you know other stuff like priority. You know, there's a whole bunch of attributes that you have for sprites. And what most people try to do is they try to create a consolidated memory that has all that in one go. So like if you're scanning through sprites, like let's say the system supports 128 sprites, for example, you have 128 addresses that have like 64 bits or 128 bits of data that it can return to you. So you get all the properties at once instead of doing like 6 or 7 calls, right, to get the stuff that you need, right? I mean, even if it's but most of the time I'm not doing that. In this Technos one, I do that. In Rising, I don't do that, primarily because that's just not. I mean, that's just not the way the system worked. I use it if I feel like I need to save time, like from a system, like let's say the system is latent and I want to save time, then I start going for that. If I feel that I'm ahead of time, I don't do that. I just do it the normal way, the way that it would normally be done on the board, whenever possible. Sometimes you need to cheat a little bit and consolidate, but most of the time I'm not doing that. I'll do it like in the normal way the board does it. Okay. All right. So that's that. So you need Cortis, obviously, 21.1 preferably, or later. And so you have that. Let me show you ModelSim. Okay. So ModelSim is something that I use. I got it many years ago. I got it legitimately, I would say. But like basically ModelSim is something that I use and I have used extensively for many years now. I've tried other you're not locked to this, by the way. My simulations should work on other simulation tools, but they're Verilog based simulations, just to let you know. They're not like like there are tools that you can use for simulation like Verilator, right? But you have to write your stuff in C, right? You could write, and that's perfectly fine. You can do that if you want. I'm just telling you I don't do that. That's not that's not really what I want to do, because normally I work out of the test bench for 90, 95, 90, yeah, probably 95% of the project I'll work from the test bench. The last 5% I'll probably do trial and error on the FPGA if I'm seeing differences. But most of the time I'm going to do stuff in simulation, and so I want, most of the time, since I'm working in the test bench, I want to be able to transition that to the actual core. Like if I'm messing around with something in simulation, I want to be able to transition that to the core. I don't want to be writing C code and then porting that C code to Verilog and then verifying it and then working out issues, then going back to the C. Like it's like just going to be a mess. I'd rather use the legit modules that I'm gonna do, for the core, and then just transition them along. So since everything's in the same language, I can do that in Verilog. And ModelSim is an extremely powerful tool. I use it all the time, and it supports TCL scripting. So a lot of the test benches utilize TCL scripting that I've put together for you. So if I can show you here, whoa, can you see that? I don't know if you're going to be able to see this. This is pretty old. So like to run, there's three simulation benches that I've included in the course, and those are the three simulation benches that I use. I only use three. Okay, and they're all variants of the same one. And they all get started by doing do sim.do, and then there's three possible ones. There's full sim, game sim, and video sim. Yeah, full sim, game sim, video sim. Those are the only three test benches that I need to make a core. The only three. Okay. Video sim is for uh, just testing the video chain of the core, right? Because often at times, graphics is a separate and independent subsystem. Yeah, there are some parts that might report back to the CPU, but generally speaking, the frames are generated independently, okay, through a video chain, right? There's a line counter. There is like some graphics processing. Maybe you're getting something from ROM. You're getting bitmap data. You're mapping it, or drawing it at coordinates, like stuff like that, right? That's all an independent subsystem. It has nothing to do with CPU. The CPU determines what work to do by putting it into RAM, right? That may be some sort of video RAM. Sometimes there's a consolidated RAM that it uses, and you have to copy stuff over. There's different sorts of situations, but generally speaking, video sim is the one I use the most because I'm going to be dialing in the pixels. I want to make it pixel perfect, so I usually spend a lot of time in video sim dialing the pixels in for different cases. So I'll go to Maim, and which is, by the way, another, like I said, I've said this many times, you need the current working emulators to do proper research for whatever core you're doing. So download Maim, download Final Burn Neo. Make sure you get a developer setup going, because you're going to want to mess with code and mess with different sorts of things within them, and do things properly that way, and do your research and try to figure out how the system works before you implement it. So anyway, yes, I use dumps from there. I restore the memories here, and then I run my video chain for a particular scene that I am researching, right? If there's a scenario that my thing just draws the wrong thing, or draws bad things, right? Then I'm going to want to get to that point using the emulators, and then what I will do is I will constantly run video sim to dial that in while I change the Verilog. Okay. And then there's two sims that I use in the early phases of the project when I'm trying to like get the whole system working, which is full sim and game sim. So full sim, basically what that is the loader plus the main core, right? So before you actually run your core, there's a loader that has to be made, right? Because if your game is large, right, you're going to want to load some of that data to SDRAM, for example, or DDR memory, or BRAM. Sometimes your game is really small and you're doing like, well, not, yeah, maybe Pac-Man or some smaller game, right? That fits in block memory, but you want to load it somewhere, right? You can't like you can't like access it from an SD card. That's not gonna. I mean, I guess it could work, but like basically it's too slow, right? And it's not practical for that purpose. And it's not even proper for that purpose. If you're doing something like that. So like basically you're gonna want to load your data somewhere. So there's a loader step that is covered in the full sim. In the game sim, it assumes that your assets are already preloaded to wherever you want. So you start out like with the loader already done, and you just want to simulate. Okay, what does this core look like when it starts up? You start with the CPU, right? It's going to run the CPU. It's going to run the whole system as a whole, right? Because everything's all continuous in Verilog, right? So it's going to run the whole system as a whole, but it's just not going to run the loader step. So I do the full sim first. Make sure my loader is proper, that it's loading correct data to everything. And then I transition myself to the game sim where all my stuff is preloaded. Okay, I'm done with that step. I verified it. I'm not going back to that again unless I change something. And then I'm gonna verify that the CPU works, that all the subsystems work, all the cross communication works, because oftentimes you have a different sound CPU than a main CPU, and they're all communicating together, right? So you want to verify the interfaces. You want to verify the communication strategies that they use to communicate with each other, and that sort of thing. Okay, so that's what I use that for. Now, so that's ModelSim. I'm not going to really talk too much about this at this stage. When I take you through the full core example, I will run stuff in ModelSim for you and explain to you what's going on. But for the moment, just note that I use ModelSim to do my stuff. Okay, and I use it for most of. No, I don't use any other tool. I only use ModelSim. Okay, so the next thing that I want to really touch on is Maim. Okay, Maim is a very powerful tool. I use it sometimes for no, I use it all the time for research, just not as much as Final Burn Neo. Final Burn Neo should be used also. I think because you can modify the code easier. The interfaces are less abstracted, so you don't really have to go through many layers to modify the thing you're trying to modify to test or learn the system. So I suggest using Final Burn Neo from that perspective. But I use Maim for a different purpose, and I'll show you what I use it for. Whoa. Let me see here. Maim. Let's see here. I am not doing this very well right now. Let's see here. Maim. Let's see. Maim. All right. Maim. Why is it that I can't ever find Maim when I need it? Oh, it might be on desktop actually. Here we go. All right. All right, so Maim. So basically, let me see here. So for example, if I was trying to run narc, right? All right, so this was actually the last setup I had on narc when I worked on it before. But basically, what I use Maim for is the disassembler. I use it for breakpoints. But basically, what I'm doing in Maim is I only use it for troubleshooting the program, right? So I'll have assembly here, right, that I'll use, and this is TMS assembly, obviously. Maim is extremely good at debugging assembly code. I like it for that purpose, and I do have to do that a lot of times. It's good to edit memory. I do that in Final Burn Neo too as well, using the Visual Studio tools. But you can do that here in Maim too. It's good at exporting disassembly. So one technique that's very often overlooked is using the original assembly to infer what the board is doing, right? So, like, yeah, for the cores that we do, we have the boards for sure. Like, we don't usually do cores that we don't have the boards for. We need the boards, right? Um, there's only so much you can get from the board, though, right? Like, so what you can get is you can get I mean, you can get timings, you can get video timings, you can get some specific chip logic when treated as a black box. Obviously, you can do decaps, but that's destructive, right? You have to break the chip to do that, and there's other sorts of things you can get from the board, and most of the time, what we do is we play the board extensively to get a feel for it, and then we play the core extensively to confirm it matches the experience, right? That's what we normally do most of the time in our workflows. But there are some things where I have to research it, and I need access to the assembly. And like I said, one of the techniques that's often overlooked when people do FPGA cores is they don't look at the assembly. And that's a very powerful piece of information because if you have the assembly code for the game, you can infer how the game was using the board, right? And you can infer, therefore, what the board was actually programmed to do. And there's a lot of issues that I've resolved and that even are like issues that exist in current emulators today that I've resolved, in our FPGA cores that use this technique, right? That I would go to the assembly code, I would debug the assembly code, and I would try to infer what the board actually is doing, because if you have a program that's written for the board and you step through the assembly and figure out, what the assembly code is doing, then you can infer, therefore, what the hardware capability is or how the feature is supposed to be used, right? If you're researching a very particular area. But also, nowadays with AI tooling, you can like export assembly from Maim and you can just put it in an AI tool and you can ask it questions about how things work in the assembly code, right? So there's a lot of things you can do with assembly code that's very powerful that people often overlook, and I use that. I use that for research. Okay, so that's Maim. So that's what I use it for. I use it for inspecting and sometimes exporting memory. I use it for assembly debugging, which is right here. I often have many memory windows open. These are my breakpoints for this. And I often use this because I want to inspect the state of the processor, right, at the time that I'm doing it. Now for Midway, for the TMS 34010, I actually created my own CPU core for this. I have not released it because I'm still working on other cores related to this, like the T unit and the V unit and so on. I'm sorry, T unit and Wolf unit. So basically, I have not released this yet, but what I did from a simulation perspective is I could actually take the state here. These are the registers of the CPU, right? A stack pointer, the state, and the program current PC program counter. And I could take the full state of this CPU and restore it to the test bench. So this way I could actually get the emulator to a certain point of where my issue was. I could export the state of it and try it in the test bench and see what's breaking. I researched some problems that way. Okay. So that's that. That's Maim. Whoa. Yeah, that's Maim. And then basically, I think that's about all the tooling that I recommend to use. So if you're following this series, make sure you have those tools in place. I suggest getting familiar with them, and then the next video, hopefully, once the code bases are ready for public consumption, we'll start going over them piece by piece, and I'll cover the entire project, right? So I'll cover Double Dragon 3. We're going to be releasing all three, but like basically we'll start with Double Dragon 3 because that's, then we have to get the other code bases up to speed and port them and that sort of thing. Not port them, but like basically we've already ported them, but like basically just polishing them and making them digestible for public consumption. And so I'll cover those in the next video, hopefully if they're ready, and we'll start diving in, and we'll take a look at the whole project, right? The whole project from start to finish. From getting the framework set up, getting familiar with your FPGA device, how do you use it, how do you run things on it, all the way down to how do you program your CPU, how do you program like different subsystems, like pretty much the whole thing. So we'll see you in the next video.